Hello and welcome to Creating an Immersive World with Audio, a deep dive into advanced audio implementation using Wwise and Unreal Engine. Today we will be exploring an Unreal demo called Old West, and how I used Wwise and Unreal to transform it from its default state without audio to an immersive Old West inspired world full of sound and light. Let's jump in. To start, let's just take a walkthrough of the level itself to hear the finished product. Before we hop into the technical details of how I made this level, I want to warn everybody, this is a long one. Creating the audio for this level took a very long time, and there is a lot to go through. Please feel free to check the timestamps in the description to jump to the section that you are most interested in. If you want to see it all, watch on and enjoy. Okay, for those of you who are interested, I'll now go into the technical details of everything that's happening in the demo and how it works. Let's start out with the ambience beds. The primary beds are the room tones for the church and factory, along with an ambisonic bed for the outside. Here you can see the outdoor wind sample being shaped with an automated EQ to simulate wind. Above it here are some birds and coyotes to fill out the ambisonic field a bit more. Next up, I created the room tones for both the factory and the church. The factory room tone was made up of a looping 2D bed. along with some large metal creaking samples meant to be played in a random container within Wwise to add texture and variety to the room tone. And as for the church, it was simply a 2D bed full of large wooden creaking sounds. Finally, as a fun bonus, I decided to add a 2D fly that occasionally flies around the player's head. Okay, now it's time to bring everything into Wwise to prep it for implementation into Unreal Engine. As you can see, the room tones are organized into different actor mixers based on channel type, ambisonic or stereo. This will make bussing easier as we continue to build out the level. As for the Ambisonic's outdoor bed, it has loop enabled, and the Ambisonic's actor mixer is being sent to the Ambisonic's bus for processing. On the Ambisonic's bus itself, we have it configured for third-order ambisonics with a resonance audio plugin for binaural decoding. Let's take a quick look at the stereo room tones that we created. Within the factory blend container, we will find both the bed itself and the random container for the metal creaks. These creaks are continuously played with a randomized delay between each one. We also have the fly random container within this actor mixer. Just like the metal creaks, this fly sound is playing continuously with a randomized delay. Finally, we can head into Unreal to begin putting these sounds into the game. After creating unique stop and start events for each of the room tones, I began the process of creating Wwise spatial volumes for each of the unique rooms. This would be the large outdoor volume, the geometrically challenging factory, and the church. After building these volumes, I simply attach the play events as room tones for each volume and set them to auto post. Let's take a quick listen to the finished outdoor bed. And let's not forget about the stereo fly that needs to buzz around the player's head. To implement this, I simply went into the third-person character blueprint and set the Wwise event to post on the default begin play event. Nice. Now we're going to move on to the next section of the project, creating and placing unique audio emitters around the map. A unique challenge on this map was handling the river. The river is so large that no single emitter would cover the entire object, while placing multiple emitters to represent it would cause volume and phasing inconsistencies as the player moves around. A unique solution to this issue is creating a single river emitter that is locked to a spline path that traces the shape of the river. This emitter is then coded to follow the player as they move around the map, giving the illusion of a large river with a single emitter. In order to achieve this, we start by creating a new actor that has a Wwise event and a spline component. In blueprints, we begin by posting the river emitter event and gaining a reference to the player character in the scene. We then set that reference to a variable called character ref. From there, we move on to having the Wwise event physically track this character ref variable. Using the find location closest to world location node, we can find the spot on the spline that is closest to the character ref and return the X, Y, and Z coordinates. We can then use this set world location node to set the Wwise event to this location. You can see I added a bit of height to get the Wise event off the floor of the river to avoid occlusion issues. From there, it is simply a matter of adding a small delay and creating a loop to execute this function at a controllable rate. Another option here would be to simply use the default event tick node, but this function does not need to update that frequently. Once that blueprint was created, we can now begin the task of creating the spline itself to trace the path that the Wise event will track. We are now going to move back into Reaper to create the assets for the emitters that will be placed around the level. Here's a river emitter and some various creeks that will randomly play. A challenge with this number of audio assets is efficiently naming and creating regions for them. Luckily, the fantastic sound design community has made Reaper tools to make this process a breeze. Using RNC's Create New Regions for Selected Items script, we can instantly create a region for this item with the correct name. On the other hand, for sounds with variations that need to be enumerated, I used Logan H's, aka Snoopy20111, name and enumerate regions script. Thanks, guys. Now that we've finished naming and exporting all of these audio assets, let's get them into Wise and set them up to trigger correctly. Most of these emitters that you see here are set to continuously play through the random container with a randomized delay between each sample. The foliage noise is unique in that it uses the X-fade transition mode to crossfade seamlessly between the randomized samples. This creates a sort of randomized foliage bed that never repeats. Before we place all of these emitters into the level, I wanted to show you a visual representation of how the river ambience works. As you can see here, I added an arrow component to the blueprint to let us track where it is. Let's hop into the game and see it in action. Now we can begin the tedious task of placing these emitters throughout the entire level. Finally, let's jump back into Wise and tune the attenuation curves for all these emitters. Most of these use global project occlusion and obstruction to save resources during runtime. Okay, now to hop into one of the more complex parts of this integration, setting up spatial volumes and portals to represent spaces around the map. To begin, I needed a transient sound that could be triggered at runtime to test the acoustics of the different spaces. I called this my whistle tester. It is simply a sample of a whistle set to use game-defined aux sends. It is also set to be a 3D sound with diffusion and transmission checked in the positioning tab. Hopping into Unreal, we can trigger this whistle by using the third-person character blueprint. When I press E, the sound is simply triggered at the location of the third-person character. Now we begin the process of creating spatial volumes all around the map. This process could have taken me ages if it wasn't for a tip from a mentor. By using the Poly Extrude tool in the modeling mode, I was able to outline any shape and extrude it upwards, creating a fairly accurate spatial volume quickly. Using this tool, I was able to quickly create the volumes to represent the edges and buildings around the map. Now, to actually create the reverbs in Wwise. I first set all the emitters to use game-defined aux sends. From there, it was just a matter of creating the reverb buses and tuning them for each room. Once the reverbs were tuned for each space, I just hopped back into Unreal and set each aux bus to its respective spatial volume. I also wanted to share this clip of me using Wwise to live connect to Unreal Engine in order to tune these reverbs in real time. That's probably a bit too much. Once the reverbs were finalized, I created portals to connect each of the spaces and began the long process of testing and tweaking, aka me walking through doorways over and over again. To add that next level of realism to the scene, I created a footstep system that takes into account both player speed and material. In this demo, there are 3 levels of footstep intensity based on if the player is sprinting, walking, or crouching. There are also 4 possible materials that the player can walk on during gameplay. In case you haven't noticed, that's a lot of footstep samples. You can hear in the background all the different materials. I also added a spur sample that will be added to each of the footsteps in Wwise, since we are playing a sheriff after all. The hierarchy here in Wwise is very important to how the footsteps function. Within the Foley actor mixer, we have the footstep actor mixer. In here, we have the spurs random container and the step switch container. You can see within the step switch container, we have all the materials that the player could walk on in-game. Each material is its own switch container housing the respective sprint, walk, and sneak random containers that it could need to play if it is chosen. In the Game Syncs menu, I have created 2 switch groups to house all the footstep material and player speed switches. These are then assigned to the switch containers that they should control. Finally, let's start choosing some switches and test the system to see if it is selecting the correct random container to play. Hopping over to Unreal, the scene does not have a sprint or sneak function built into it, so we will need to build that ourselves. We will also need to use this new logic to set the footstep intensity switch in Wwise. In the third-person character blueprint, I first created 2 Boolean values to represent if the player is sprinting or sneaking. If the player is holding shift, sprinting is true. If the player is holding control, sneaking is true. This allowed me to make custom sprint and sneak speeds for the player based on these conditions, using branch nodes. These 2 booleans will also be valuable later. While creating the sprint and sneak function, I also set up a variable that tracks the length of the forward vector of the player. This is set to a float variable called player speed. By casting a reference to it in the animation blueprint, we can then set the player speed RTPC in Wwise. This RTPC will be useful later. You can see down the line is where we use those booleans from earlier to set the player speed switch, which is what controls the footstep velocity. Now we need to set the correct physical materials for each of the objects that the player could walk on. Over in the project settings, we start by creating 4 unique surface types. I then created 4 physical material objects and assigned these surface types to those physical materials. Now it is just a matter of going through the level and assigning these physical materials to the materials of the objects that the player will be walking on. Now that all the physical materials are set up around the level, we can now use blueprints to set up the logic for the footstep material switch. Within the detect player footstep material function, I have set up some logic to send a raycast directly down to the player's feet. This raycast then detects the surface material that it hits, and after some conversions, it sends that value to Wise to change the switch. I'm going to set up a print string node here so that we can see it in action. Almost finished with the footsteps. To trigger the footstep event, I set up animation notifies within the walk and run animation of the player. These notifies will be used to start the entire chain to set the switches for the footstep intensity, material selection, and eventually to trigger the sound of the footstep itself. On to the final feature of this demo, the dynamic foley movement system. The concept for this system was pretty simple. A foley movement system that scales up in intensity as the player increases movement speed. The idea is to use that player speed RTPC that we created earlier to increase the volume and open up a high and low pass filter on the foley sounds within Wise. In order to start this process, I created some movement and cloth sounds. I collected some equipment, metal details, and leather jacket sounds to represent the sheriff that we play in game. You can hear those samples in the background now. Once those samples were created, it was then time to bring them into Wise and set up that RTPC to control the movement intensity. You can see here within the movement blend container that we have the random containers for both the equipment and leather jacket sounds. You can also see the RTPC on the movement blend container to scale up the volume, pitch, and reduce the low pass when the player speed RTPC increases. In order to implement the movement sounds into Unreal, I created animation notifies on the player walk and run animation in order to trigger the movement sounds. Moving over to the logic, you can see here what I mentioned earlier, casting to the third person character blueprint to set the player speed, RTPC. From there, the final step is to trigger the movement sound after the footstep sound, and we are all set. Before calling it on this project, I wanted to take the implementation within the scene one step further. I wanted the foliage sounds to dynamically react to the ambience outdoor bed. In other words, just like in real life, as the wind speed increases, or the bed amplitude, I want the volume and pitch of the foliage emitters to increase. Okay, that's a great idea, but how do I pull it off? The key here is an effect in Wise called Meter. This Meter plugin has a feature where you can create a parameter that's tied to the amplitude level that the meter is reading on any object. All you need to do is set the range of the meter that this parameter is using, and boom, you have a parameter that is dynamically linked to the volume of the wind. This parameter can be used for all sorts of things, but in this case, I'll use it to increase the pitch and volume of the foliage sound. You can hear that as this parameter increases, the pitch and volume of the foliage increases with it. If you sat through this entire video, I thank you, and I hope that you learned something new. It was such a unique learning opportunity for me, and it showed me that if I set out clear goals and a vision for a project, achieving it is just a matter of time. Please feel free to contact me with any questions, and thank you for watching.